In this video, we're going to be looking at topic 1C, which is energy and specific calculations as part of the IAS chemistry course from Edexcel. So we're going to be looking at a number of different outcomes, so how we can understand the terms relative atomic mass, molecular mass, formula mass, and molar mass, being able to perform calculation using Avogadro's constant, to be able to use chemical equations to calculate reacting masses, and how to calculate percentage yields and atom economy. Now, some of these you will have met at GCSE, so they should just be revision, but a few points will be new, specifically atom economy. So we'll go through how to do these calculations, as well as some examples and a past paper question at the end. So when we're talking about the relative atomic mass, this is how we can compare the mass of substances. And there are a couple of different key definitions that we have to know. So the relative atomic mass, or AR, is the weighted average mass of an atom compared to 1/12 of the mass of carbon-12. So an atom of carbon-12 is the standard mass, and every other mass of an atom is compared relative to carbon. That's why we call it relative atomic mass. The relative molecular mass, or MR, is the sum of all of the relative atomic masses of an atom in each molecule. So for example, if you had NaCl, the relative molecular mass of this substance would be the mass of sodium plus the mass of chlorine. Relative formula mass is pretty much the same thing. It is looking at the sum of relative atomic masses of each atom in a formula. And again, we give that MR, and that could be for molecules or for ions. And molar mass, which is just a capital M, is the mass of 1 mole of a substance. So you should have learned at GCSE how to calculate these using isotopes, and you also discussed that in topic 2, so we're not going to go into too much detail about this at the moment. What we are going to look at is something called Avogadro's constant. Now, Avogadro's constant is how we scale up from atoms, molecules, and ions up to grams. Because when we're trying to work out the mass of atoms, ions, and molecules, these are too small for us to work with. So at GCSE, you'll have just said that carbon weighs 12 grams. Now, strictly, that's not true. What we do, though, is we scale that up just to make the calculation easier. And the way that we scale it up is we use Avogadro's constant. And the value is 6.02 times 10 to the power of 23. And this is the number of the particles on 1 mole of any substance. Okay? And it would be any monatomic substance if it was number of atoms. If it was number of molecules, it would be any molecule. And if it was number of ions, it would be a single ion. So for example, if we have 4 grams of helium, which is 1 mole of helium, that contains 6.02 times 10 to the 23. Carbon dioxide has a molar mass of 44 grams, and that contains 6.02 times 10 to the 23 molecules. Nitrate, NO3, in 1 mole is 62 grams, and that contains 6.02 times 10 to the 23. So this number is the constant that tells us how many particles are in a specific number of moles. And what we can do is we can use a triangle, similar to the mass triangles that you met at GCSE, to tell us how many particles are in a specific number of moles. So Avogadro's number, 6.02 times 10 to the 23, this is a constant value. Okay, so it does not change. So what we would be working out would either be the number of particles or the number of moles. So let's look at an example. I want to know how many water molecules there are in 1.25 grams of water. So I can work out how many moles that is using my mole triangle. So I do 1.25 divided by 18 because that's my molar mass of water, and that tells me that there is 0.0694 moles. If I go back to my triangle, To work out the number of particles, I take my number of moles and I multiply it by Avogadro's number. So 6.02 times 10 to the 23 times my number of moles is 0.0694, and it tells me that there are 4.18 times 10 to the 22 molecules of water in 1.25 grams. If I want to know what is the mass of 100 million atoms of gold, that may sound like a lot, but in actual fact, that is a very, very small mass. So if I go back, we can see that to calculate the number of moles, I do the number of particles divided by Avogadro's number. So 100 million is 100 times 10 to the power of 6. I divide that by 6.02 times 10 to the 23, and that gives me 1.66 times 10 to the minus 16 moles. Very, very small number. And I multiply that by the relative atomic mass of gold, and that gives me 3.27 times 10 to the minus 14 grams. So whilst 100 million atoms may sound like a lot, it is actually a tiny, tiny mass. So when we're comparing different chemicals, we can't just simply compare gold to silver or to carbon or to oxygen, because all chemicals are going to weigh different amounts. Some are very light and some are much heavier. We always want to look at the number of particles. If I take 12 grams of carbon, that's not going to have the same number of molecules as 12 grams of oxygen. So what we do is we use this fixed amount called the mole. And 1 mole of any substance is going to contain the same number of atoms or molecules, and the number is very large, you can see that there, and it is 6.02 times 10 to the 23. So 1 mole is Avogadro's number. If you have that Avogadro's number of particles, you have 1 mole. And we can use this concept to then calculate the mass or the number of moles or the molar mass of a substance. So you've met this triangle back in IGCSE. So the number of moles is equal to the mass divided by the molar mass. So for example, if I have 6.51 grams of sodium chloride, I divide that by the molar mass of 58.5 and I get 0.111 moles. Or what's the mass of 0.263 moles of hydrogen iodide, which is Hi. I take the number of moles and I multiply it by a mass of 127.9 and I get 33.6 grams. So this should be simple revision for you, but if you want to have a go at some of the questions, you can look in the A-level textbook and there's some examples there. Now, what we sometimes have to do is to use balanced chemical equations to determine the number of moles or a mass of each reactant used in a reaction, or the number of moles or masses of a product that is being formed. And in order to calculate these values, we follow 4 simple steps. And these work regardless of whether you are calculating a mass, a volume, a concentration, or even if you're doing titrations, which you will cover later on in A-level. So these same 4 steps do happen all the way through, so you should make sure that you feel confident doing these. Again, you should have covered this at IGCSE, but we'll run through some examples. So the 4 steps are, first of all, to write a balanced chemical equation. Secondly, determine the number of moles of the known substance. Now that means the information that you're given from the question. You then use a mole ratio to determine the number of moles of your unknown substance. This is where your balanced equation is used. And then you can determine the mass of the unknown substance. So let's look at an example. So here we want to calculate the mass of calcium oxide that is formed when 25 grams of calcium carbonate is decomposed. Now notice as I went through the question there, I was underlining the key information that you're given here. That's the best way to tackle a question like this. There's going to be a lot of information in the question that you don't need. You want to just pick out the key values and compounds that you need. So the first thing that we do is we write the equation for the thermal decomposition. So we have CaCO3 for our calcium carbonate, decomposing into calcium oxide and carbon dioxide. That is already balanced, so now I can move on to step 2. So the known substance is the one that I'm told something about in the question, and in this case it is the calcium carbonate. Now I can work out the number of moles by doing 25 from the question as my mass and divide it by the MR of 100 to get 0.25 moles of calcium carbonate. I then look at my mole ratio, and to do that I have to look at the coefficients in my equation. Now notice that there is no number in front of the calcium carbonate or the calcium oxide, which means they have a 1-to-1 ratio. That tells me that if I have 0.25 moles of calcium carbonate, I am going to make 0.25 moles of calcium oxide. Now I can go to step 4 and I can look at calculating the mass of the unknown substance being the calcium oxide. So I've just worked out that the number of moles is 0.25. If I multiply that by the mass of calcium oxide of 56, I get a mass of 14 grams as my answer. Another example, we've got 32 grams of methane being burned, and we want to know how much water is being formed. So this is a basic combustion reaction, and we make the assumption that it is complete combustion because it doesn't say otherwise in the question. In an exam, because you will have already studied the alkanes in topic 4 and of course at GCSE, it's unlikely you would be given this equation. You should be able to write it and balance it yourself. So you've got CH4 plus 2 oxygens giving you 2 waters and carbon dioxide. So our equation is now balanced, so we move to step 2. My known substance in this case is the CH4. So I take the mass of 32 from the question and I divide it by the MR, which is 16, giving me 2 moles of methane. This time again, for my mole ratio, I need to look at my coefficients. I have nothing in front of the CH4, but I have a 2 in front of the water. That means for every 1 mole of methane that reacts, I make 2 moles of water. So if I have 2 moles of methane, I have to multiply it by 2 to get 4 moles of water being formed. Then I can calculate my mass of my unknown substance, or the water in this case, and the mass is 4 moles times the MR of 18 to give me an answer of 72. One last example that's a bit trickier. So copper forms 2 oxides, and both oxides can be converted to heating with hydrogen. An oxide of copper is heated in a stream of hydrogen to a constant mass, and the masses of copper and water that is formed is 17.6 and 2.56. What is the equation? So this time we're having to work backwards. So in this case, the first thing that we have to do is we have to figure out our molar mass. So for copper, we can read it straight from the periodic table, it's 63.5, and for water, it is 18 grams per mole. From that, then I can calculate my number of moles. So my number of moles of copper, remember, is the mass divided by the molar mass. So 17.6 divided by 63.5, giving me a number of moles of 0.277. And for water, it's 2.56 divided by 18, giving me a mass of 0.142. Then I do a modified version of step 3. I this time use those number of moles to work out my ratio. And 0.277 to 0.142 is a ratio of 2 to 1. So that means that the equation has 2 moles of copper and 1 mole of water. So that must mean that my products are 2 moles of copper and 1 mole of water. Therefore, working backwards, it's reacting with hydrogen, and my compound must be Cu2O because that gives me my 2 to 1 ratio of my products. If it was CuO, so if it was copper 2 oxide, that would give me a formula of CuO, and that would give me a 1-to-1 ratio of copper and water. So because I have a 2-to-1 ratio, my answer is copper 1 oxide. Now, generally when we carry out experiments, the reagents are mixed in the correct proportions. So we know exactly how many moles of a substance it takes to react with how many moles of a different substance. But sometimes, for various different reasons, reactions have to be carried out where one of your reagents is in excess. What that means is if it's an excess, it means that we have more than we need to react with your other reactant. So for example, if I have A plus B to make C and D, I may put in an excess of B, which means I know for a fact that all of A is going to be able to react because I'm using more than enough B in order to make my products. So we call, in this case, B would be an excess, and A would be called the limiting reagent. Now, in an equation, you may be asked to calculate which reagent is in excess, and this involves using your mole triangle and using mole ratios. So again, let's look at an example. We have got 3.2 grams of copper reacting with 0.4 moles of nitric acid. Determine which reagent is in excess. So the first thing that we need is a balanced chemical equation. You must always have a balanced equation, or else you cannot do this question properly. So in this case, we have copper reacting with 4 moles of copper nitrate to make with 4 moles of nitric acid to make 1 mole of copper nitrate, 2 moles of water, and 2 moles of nitrogen dioxide. Now, we don't care about the products after this point. We simply use the products to get our balanced equation. Now we are focused solely on the copper and the nitric acid. So I need to determine my mole ratio, which I get again from my coefficients, and I can see that I have 1 mole of copper reacting with 4 moles of nitric acid. Now I need to determine how many moles are actually reacting. Well, I'm told it's 0.4 for the nitric acid, so that is fine. But for the copper, I need to calculate it. So I'm told I have 3.2 grams, and I divide that by 63.5 of a mass to give me 0.05 moles. Now we look at what's known as have and need. So have is what you actually have from the question. So from the question, I am reacting 0.05 moles with 0.4 moles. The need would be if all of your copper or your nitric acid reacts. Now, it doesn't matter which way you do this, you're always going to get the same answer. So in this case, we're going to say that we're reacting all of the copper. So if I wanted to react 0.05 moles of copper, I would need 4 times that, because my mole ratio is a 1-to-4. So I would need 0.2 moles of nitric acid. Now, because I only need 0.2 and I have 0.4, that means that my nitric acid is in excess, whereas my copper is limiting. Okay, so my limiting reagent would be I've reacted all of my copper, and that now once it has all reacted means that the reaction would stop. So it limits the rate and limits the extent of the reaction. So you're always looking for which one you have more of than what you need. Moving on to percentage yield, again, you will have covered this in IGCSE. So a percentage yield is the ratio of the actual yield of a product, or how much product you actually made, versus the theoretical. So in other words, it's how much you make compared to how much you should have made. And we use this equation here. So if we look at an example, the manufacturer uses the reaction to obtain methanol from carbon monoxide and hydrogen. So you can see we have 1 mole of carbon monoxide reacting with 2 moles of hydrogen to give us 1 mole of methanol. The manufacturer obtains 4.07 tonnes of methanol, starting from 4.32 tonnes of carbon monoxide. Calculate the percentage yield. Now, this is a typical percentage yield question because they will give you just the information and you need to then figure it out. So the first thing you do is you calculate the theoretical yield, and this is reacting masses, or in other words, a calculation using the balanced equation. So this is your 4 steps. So step 1, your balanced chemical equation, done. Second step in our method was to calculate the number of moles of the known substance, which is here as our carbon monoxide. So I have 4.32 times 10 to the power of 6 because that's what tons is. Tons is times 10 to the power of 6 in terms of grams. And I divide that by the molar mass, which is 28, giving me 1.54 times 10 to the minus 5 tons. I then do step 3, which is my ratio. So I have a 1-to-1 ratio between carbon monoxide and methanol. So therefore I have 1.54 times 10 to the minus 5 moles of methanol. And then the last step in our 4 steps is to calculate the mass of the unknown. So 1.54 times 10 to the minus 5 moles times a molar mass of 32 gives me 4.94 times 10 to the power of 6. And that should be grams, not moles. That's a misprint. Apologies. So that's our theoretical. This is the theoretical yield. Now we're told the actual yield in the question because we're told that we make 4.07 tonnes. So to work out my percentage yield, I do my actual yield, 4.07 times 10 to the power of 6, divided by the theoretical yield, 4.94 times 10 to the power of 6, multiply it all by 100 to get a percentage, and you get a percentage yield of 82.4. Now, atom economy is linked into the percentage yield, and it is linked into how we scale up our reactions from laboratory reactions up to full-scale industrial processes. So we have to take into account the percentage yield of a reaction, but we also have to take into account what's known as atom economy. And atom economy is the ratio between the mass of the desired product and the mass of all the products formed. So for example, if you make products in a particular reaction and you only want one of them and you make 5 other products that are wasteful, that's not very economical. So that's not going to be a good business plan for an industrial company who's wanting to make a product. You want to be able to make your product with as little waste as possible. So the atom economy is a quantitative measure of that. If we have a reaction that only makes one product, it's going to have an atom economy of 100% because the mass of the desired product is going to be the same as the mass of all the products. And making these additional unwanted products will reduce the atom economy. So we calculate it using this equation. So we have the molar mass of the desired product, and we divide that by the sum of the molar mass of all products. And in this, we must remember the coefficients. So if you make 2 moles of a product, you need to take that into account when calculating your atom economy. And we'll look at an example in just a minute. Some generalizations about the different types of reactions. Addition reactions only make one product, so addition reactions are going to have an atom economy of 100%. Elimination and substitution reactions are going to make at least two products. So they're going to have a lower atom economy, maybe somewhere in the region from 75 up to 90, just depending on the molecules. If you have to have multi-step reactions, your atom economy gets even lower, and you could be down at 20, 30, 40, or 50% atom economy. So let's have a look at an example. Sodium carbonate is an important industrial chemical manufactured by the Solvay process. And the equation is here. A manufacturer starts with 75 kilograms of calcium carbonate and obtains 76.5 kilograms of sodium carbonate. In this case, we're calculating the percentage yield and also the atom economy. So we can calculate the theoretical yield using our same four steps, and we get a value of 79.4 kilograms. My percentage yield is therefore what I actually make. So remember, this is your actual yield divided by the theoretical yield, and I get a percentage yield of 96.3%. Now that is a fairly high yield, so that would be something that is very good for an industrial process. But if we look at the atom economy, we can see that we make 106. So our molar mass of sodium carbonate is 106, but I also make the calcium chloride as an unwanted byproduct. So this is not a desired product. So my total sum of the products is 106 plus 111.1. And when I do my mass of desired over my total mass, I get an atom economy of 48.8. So whilst this process has a high yield, it has a pretty low atom economy. So what a business may choose to do is they may choose to use that calcium chloride and sell that for another purpose. So they may make the calcium chloride as a byproduct, and rather than using it themselves, they may sell it to a company that may use it so that they still get money from that. It's unlikely a reaction with this low of an atom economy would undergo an industrial process without there being some sort of plan for the unwanted product. So second example, we have a manufacturer of ethene who wants to convert ethene into 1,2-dichloroethane, and is looking at two possible reactions. So we have reaction 1, where we're adding in the chlorine to our ethene to give us our product, or reaction 2, where we're reacting the hydrochloric acid with oxygen to give us our product plus water. And without even doing any sort of equation, we can give an answer for which one is going to be the best in terms of atom economy. And the reason for that is we look simply at the number of products. This one has one product, and this one has two products. Anything with one product is automatically going to have a 100% atom economy. Reaction 2 is going to have a lower atom economy, and the reason for that is because we form this additional product of water, which has no value to the company or the manufacturer who wants to make this. So any company will always want to choose a most direct route to have a reaction with the least amount of waste byproducts. So that's all the different calculations that you're going to use. Let's have a look at some example past paper questions. So what you may find is that past paper questions for calculations are very commonly your multiple choice questions. They will come up through the written paper, of course, but typically the bulk will be in your multiple choice. So for this from the June 2019 paper, the value of the Avogadro constant is equal to the number of, and it's finding one of these two. So we have to look at, is it A, the grams of carbon in 1 mole of carbon? Well, we know that Avogadro is nothing to do with grams. It is not a mass, it is about the number of particles. So it cannot be that answer. So that leaves us with B, C, and D. For B, it's looking at the number of atoms in 1 mole of oxygen gas. Now, if that was the case, that would be telling us that oxygen gas contains 1 atom of oxygen. Now, we know that oxygen is diatomic. So if I have 1 mole of that, I have actually 2 times Avogadro's constant. So that can't be the answer. For C, is it the number of atoms in 1 mole of helium gas? Well, helium gas only contains 1 atom. So the answer is actually C. But let's just confirm by looking at D, and D would be the number of ions in 1 mole of sodium chloride. But again, similar to oxygen, sodium chloride contains 2 atoms, it contains 2 ions. So that would mean that in this case, for 1 mole, it would be 2 times Avogadro's constant. So your answer here is C. For number 6, we have how many electrons are in 10.1 grams of neon. So I first of all need to figure out how many moles that is. So I've got 10.1 divided by a molar mass of 20.2, which gives me 0.5 moles of neon. How many particles is that? Or how many atoms or particles, either one would be acceptable to say. We've got 0.5 moles times Avogadro's number, 6.02 times 10 to the 23. So that's going to give me 3.015 times 10 to the 23. And then for the number of electrons, well, I have to check the atomic number, and the atomic number of neon is 10. So I'm going to multiply my number of particles. If I have 3 times 10 to the 23 particles, each of them is going to contain 10 electrons. So my number of electrons is going to be 3 times 10 to the 23 particles times by 10, which gives me an answer of 3 times 10 to the 24, meaning my answer is B. So there you go. You can see the answers there are C and B, as we said. So this is from the January 2018 paper, and this time we're looking at a calculation from balanced equation between phosphorus and 6 moles of iodine to make 4 moles of phosphorus 3 iodide. And this is a slightly trickier example because it does require quite a bit of working, and unfortunately it is only for 1 mark. As you will find in A-level, something that was worth maybe 2 or 3 marks at GCSE is now probably only going to be worth 1, maybe 2 at most. So we want to calculate the minimum mass of iodine required to produce 1 kilogram of the phosphorus iodide when phosphorus is in excess. So we are not interested in the phosphorus anymore, we are only interested in these 2 things. So I have my balanced equation. So the first step I do is I calculate the number of moles of the known substance. In this case it is my phosphorus iodide, or my Pi3. So my mass is 1,000 grams, because remember I have to put it into grams because my molar mass is in grams per mole, divided by 411.7, and that is going to give me an answer of 2.42895 moles. You'll get a long number on your calculator, of course. Just make sure you store that number, and that's the number that you're using here. Here we've got a 4 to 6 ratio. Now this is a bit of a tougher ratio because it's not just as simple as a 1 to 2 or a 1 to 3 ratio. But the easiest way to do this is we divide by the first number in the ratio and we multiply it by the second number. So to get my ratio, I do 2.42895 and I multiply by the second number and divide by the first, and that is going to give me an answer of 3.6434 moles of iodine. Then I can work out my mass as my number of moles times my molar mass. So I have 3.6434 times the molar mass of I2 you can get from your data book is 253.8, which gives me an answer of 924.7, but remember that is in grams. So if I want to convert it into kilograms, it's 0.925 kilograms, giving me the answer of B. Then I want to look at a similar sort of question where it is the sulfur reacting with chlorine to produce sulfur dichloride, and we want to know the maximum amount of mass of sulfur dichloride that can be produced from the reaction of 0.1 moles of sulfur with 0.39 moles of chlorine. So what this is actually asking me to do, firstly, is an excess calculation, followed by a reacting masses calculation. So I have to figure out, firstly, which one is my limiting reagent, because the limiting reagent is going to determine how much product I make. So I look at my sulfur to my chlorine, and I can see that I have a 1:4 mass. So that is my ratio of my moles. What I have is what I'm told in the question. I have 0.1 and 0.394. Now, if I wanted to react all of the sulfur, my need would be 0.1, and I would need 4 times this, so I would need 0.4. Now, I only have 0.394, so that tells me that the sulfur is in excess, and my limiting reagent, therefore, is the chlorine. So my number of moles of chlorine is going to determine how many moles of the sulfur dichloride I make. So now I look at the sulfur and the disulfur dichloride and the chlorine, and we can see that they are in a 4:4 ratio or a 1:1 ratio. So that means if I use 0.394 moles of chlorine, I must make 0.394 moles of dichloride disulfur. And I want to know the mass, so I do 0.394 multiplied by the molar mass, which is 135.2, and I get an answer of 53.27 grams, which is C. And you can see that there are my two answers of B and C. Now that's everything for the 1C topic, so your reacting masses, percentage yield and atom economy. Of course, there are lots and lots of examples that you can do on these to get better. The best way to get good at calculations is to practice. So you can use the textbook, you can use past papers, or if you simply go onto the internet and input into the internet reacting masses practice questions, you will find hundreds, if not thousands, of questions to allow you to practice this. If there's anything that you're not sure about, of course, feel free to leave a comment below, and I hope that you're going to go away and practice some of these calculations so that you are an expert, and feel free to check out the other videos on this channel.